Thank you very much. So first I want to apologize because I told you some lies in my last lecture. So the first lie was in response to a question about, in the discussion of two-dimensional topological quantum field theories being classified by commutative Frobenius algebras, there was a question about how many examples of these things there were and whether or not you might be able to write down a list or something like that. And I didn't give much of an answer, but I said maybe there aren't too many. But that's totally wrong. So remember what a commutative Frobenius algebra is. It's a finite dimensional algebra over the complex numbers, which is commutative and associative. And it's equipped with a trace map from A to the complex numbers that gives you a non-degenerate pairing. So you can think about this trace map as an element in the C linear dual of A. Now the dual space of A has an action of A. You can think of this thing as an A module. And therefore, if you've chosen an element, it determines a map from A to A dual. And that map, of course, is just an incarnation of the trace pairing. So to say that you have a Frobenius algebra is to say that you have a finite dimensional algebra A and an isomorphism of A with its dual, which is A linear. Now, so in particular, you'll have a Frobenius algebra whenever you have an algebra A, which is A linearly isomorphic to its dual. Now, there's a name for algebras with this property. They're called Gorenstein rings, or more precisely, these are Gorenstein rings of Krull dimension 0. And there's lots and lots of them. So here's an example. So take a polynomial ring on n variables and take any n polynomials you like, f1, f2, and so forth through fn. And this is an example. If this is finite dimensional, then it's an example of a commutative Frobenius algebra. So these things can be pretty complicated.
What would you take as a trace map in that case?
I think the trace map is something like you take a polynomial and then you take the residue of that polynomial divided by the product of the FIs. So trace of P is the residue of P dx1 wedge dot 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 wedge dxn divided by f1, f2 through fn. I think. I'm on camera, so maybe I shouldn't. Let me erase this. I think that's right. It's something like that. So yeah, and Heiss is taking notes. So Heiss, if you took notes about what I said at the end of the last lecture, you can erase those too. So the other lie that I told you is that in this lecture, I'm not going to say anything about Dijkgraaf-Witten theory. So that's almost right. I don't want to say much more about Dijkgraaf-Witten theory, but I didn't quite say enough about it in the last lecture to motivate what I really want to talk about in this lecture. So that's going to appear in a little while. What I'd like to start with, though, is introducing a little bit of terminology. So throughout this talk, or for this discussion now, let's say X is a topological space, and C is a category. And the kind of categories that I have in mind are, for example, the category of complex vector spaces. So let me recall the definition of a local system on X with values in C. So a local system on X with values in C is the following data. Well, let me give the local system a name. Let me call it script L. So to specify a local system, you have to specify three things. So first, for every point x in X, you specify an object, L sub x, which belongs to the category C. So in practice, maybe this is something like a complex vector space. So the second thing you need is for every path P, a continuous map from 0, 1 into X, you're supposed to supply an isomorphism. Let me call it L sub P. This is an isomorphism in the category C from what your local system looks like at the beginning of the path to what your local system looks like at the end of the path. So this is the kind of data that you would get if, for example, you had a vector, if X was a manifold and you had a vector bundle with connection. So then to every point, you're supplying a vector space, and for every path, or at least, well, every smooth path, you get parallel transport along that path, which gives you an isomorphism between the fibers of your vector bundle at the two endpoints. And third, for every 2 simplex sigma, so what I mean is a map from the 2 simplex into X, and I'm just going to draw that diagrammatically. It supplies 3 points in the space X and 3 paths between them. Let me call them P, Q, and R. Every time you have a 2 simplex giving you all of this data in the space X, we're going to have a condition, which is that the isomorphism L sub R should be given by the composition of the isomorphism L sub Q with the isomorphism L sub P. So this is a way of saying 2 things simultaneously. First, it's telling you that the isomorphism L sub P depends only on the homotopy class of the path P. Homotopic paths give the same isomorphism. And second, it tells you that when you compose paths by concatenating them, the isomorphisms also compose. So the data of A, B, and C all together is what you would expect and what you get if you have a vector bundle on X with a flat connection. Again, in the case where X is a manifold. So another way of saying this, I think Chris mentioned the fundamental groupoid of topological space in his talk. So equivalently, a local system on X is a functor L from, let me write, pi less than or equal to 1 of X into the category C. So this is the fundamental groupoid of X. It's a category whose objects are points of X, whose morphisms are homotopy classes of paths in X. And maybe I should also mention more concretely, let's say if X is connected with base point, and you've chosen some base point, little x, then to describe this local system, or to describe a local system on X, you sort of only have to say what it does at that particular point, because any other point is connected to that base point X by some path. So, well, let me say local systems on X, giving a local system on X is equivalent to giving an object of C with an action of the group, of the fundamental group of X at your chosen base point. And that action is just given by B. If you have a loop based at your point, it gives you an isomorphism of your object with itself, and condition C tells you that that is compatible with composition, so it defines an action of the fundamental group on the object you've chosen. So again, the case of interest say, is where C is complex vector spaces, and then what we're saying is local systems are just representations of the fundamental group of X. So I want to do a little example. So let's take C to be the category of one-dimensional complex vector spaces. And let's unravel what it would mean to give a local system here. So the first thing that we need to do is to supply for every point x in X a one-dimensional complex vector space. But of course, up to isomorphism, there's only one choice. So let's just say that we're going to assign C to every point. So now what else does it take to describe a local system? Well, for every path in X, you have to specify an isomorphism of the complex numbers with itself as a vector space. So this is what we're doing for A. For B, what we have to do is, well, we have to assign an invertible complex number to every path. An element of C star to every path. And these elements of C star are not arbitrary. They have to satisfy a condition that comes from C. So let's call these elements of C star something. So if we have a path P in X, well, I called it L sub P earlier. So L sub P now, let me just think of that as an invertible complex number. And C is this condition that if sigma is a 2-simplex, which is made out of paths P, Q, and R, then L sub R is equal to L sub P times L sub Q. It's just as invertible complex numbers. So there's a name for this data, which is hopefully familiar to you. This is the data of a one cocycle on X with values in C star. Namely, the data B is the data of a one chain on X with values in C star, and C is the condition that it be a cocycle. Now, it's not quite right to say that local systems, it's roughly correct to say that local systems are the same thing as cocycles. Maybe we should say local systems together with a trivialization at each point are the same thing as cocycles. But of course, that involves a choice. You chose an isomorphism of your local system with C at every point. You could choose that isomorphism differently, and if you make a different choice of isomorphism, you'll get a different cocycle. Namely, you'll get a cocycle that differs by a one coboundary. So the upshot of this discussion is that isomorphism classes of, well, let me say one-dimensional local systems on X are in bijection with the cohomology group H1 of X with coefficients in C star. And you can be more precise than this. Namely, if you want to write down a local system, you just need to write down a cocycle that represents the cohomology class that you're thinking of. OK, so I want to now go back and talk a little bit about Dijkgraaf-Witten theory in the twisted case. So let me recall a little bit about what we were doing in the last lecture. So let's say that G is a finite group. And this time, I'm going to do a twisted version of what I did last time. So G is a finite group, and we're going to consider a twisting that's controlled by a certain cohomology class. So I'm going to take a class lying in Hn of the classifying space Bg with coefficients in C star.
Maybe that's the wrong class word to use.
Is it not visible?
No.
Oh, it won't go. You're saying it.
Look down.
Ah, excellent. All right, G and eta. So this data defines an n-dimensional topological quantum field theory. And last time at the end, I said what this n-dimensional topological field theory does at the top level. I told you what the invariant was that you assigned to a manifold. So let me write that again. So let me use the letter Z for a topological quantum field theory. So what do you do on an n manifold? Well, you get a number. So let me assume for simplicity that M is connected, and well, let me write it in the following way. So this is 1 over the order of G times the sum over all homomorphisms from pi 1 of M into G. Now, giving a homomorphism from pi 1 of M into G, that determines, let's say, a pointed map from M into Bg. So I don't know what to call this. These are essentially the same piece of data. So let me just call this alpha with a bar over it. So if you have a homomorphism, it determines a map of topological spaces. And then you can take that map of topological spaces and use it to pull this cohomology class back. So this expression here now lies in Hn of our manifold with coefficients in C star. And now we have an n-dimensional manifold and an n-dimensional cohomology class. What we can do is integrate. Or let me write that as a valuation on the fundamental class of M. So this now is an invertible complex number. And the prescription is take those invertible complex numbers and add them up and divide by the order of G. Or as in the last lecture, this procedure can be thought of maybe more invariantly. What you're doing is some sort of averaging of these numbers over the collection of all G bundles on M. OK, so this is the number that you associate at the top level. Sorry?
You want to take conjugacy classes?
Conjugacy? No.
Aren't you acquainted?
No. If I summed over conjugacy classes, then I should move this inside, but it should be 1 over the number of automorphisms of the G bundle. OK, so that's the number that you assign at the top level. But this collection of manifold invariants fits into the framework of topological quantum field theories, meaning there's something analogous that we can do for n-1 manifolds that produces not a number, but a vector space. So let me now describe what that procedure is. So for this, I want to think about the space of all maps. So let's say M is an n-1 manifold. And what I want to think about is the collection of all maps from M into Bg. Or this is a classifying space for G bundles on the manifold M. Connected components are in bijective correspondence with isomorphism classes of G bundles. But it's a mapping space. So in particular, this mapping space cross M maps to Bg. And also, this mapping space cross M projects onto M. So now, here's what you can do in this situation. So you have eta, which is an n-dimensional cohomology class on Bg. So let's call this, let's give this map a name. Let's call it EV for evaluation. So you can take EV upper star of eta. That's an n-dimensional cohomology class on this product space. And now you can integrate that along the fibers. Ooh, sorry, wrong projection. This projects onto maps from M into BG. It projects onto both, but this is the map that I want to integrate along the fibers of. So this is an n-dimensional cohomology class, and M is an n-1 dimensional manifold. So I can integrate along the fibers to get a cohomology class. So why don't I call it the integral over M of EV upper star eta, and this is going to live in H1 of this mapping space with coefficients in C star. Now, we just had a discussion a little while ago about how you can think about that cohomology group. It's classifying one-dimensional local systems on this mapping space. Or it's classifying them up to isomorphism, but I could have done this a little bit more carefully. I could have said, I start with eta, not really a cohomology class, but a cocycle representing one. Then I get a cocycle here, a cocycle here, and a cocycle here. That actually lets me build this one-dimensional local system explicitly. I don't just know it up to isomorphism, I could write it down. So let's say that this constructs. So this is the same data as a local system, a one-dimensional local system, L sub M, which lives on the space of all maps from M into BG. So now let me tell you what Dijkgraaf-Witten theory is supposed to assign to M. So definition, the value of Dijkgraaf-Witten theory on an n-1 manifold, this is supposed to be a complex vector space. This is the space of sections of L sub M. So maybe I told you what a local system is. Maybe I should tell you what a section is. So, well, let me do it on this board where I'm giving very general definitions. So if L is a local system, of, let's say, C vector spaces on X, then you can define the space of sections, which I'll write as H naught of X with coefficients in L. This is the collection of all, well, let me say it like this. For every point little x, you give an element v little x inside the fiber of your local system at X. So you have to supply an element in each of these vector spaces. And let's say that these are, what should I say? Holonomy invariant, meaning these elements are not unrelated to one another. Whenever you have a path in X, the isomorphism corresponding to that path is supposed to carry the element of this vector space that you've chosen to the element of this vector space that you've chosen. So if you think X is a manifold and this thing is coming from a vector bundle with flat connection, this is the space of flat sections. So this is a complex vector space, and well, is the definition clear? Any questions about this? So this also has a more abstract description. It could make sense in the context of objects of any category. This is what you might call the inverse limit of L. The vector space, what is it? It's the inverse limit of all of the vector spaces L sub X that you've assigned to the different points under all of the maps that come from paths in X. And that description makes sense in an arbitrary category where you can take inverse limits. So that's what I'm going to mean by H naught of a local system. So sorry?
Can you say again the diagram you're taking the limit of?
The diagram, so the diagram is this one. So the local system you can think of as a functor from the fundamental groupoid of X into C, and that's a diagram in the category C, so you could take its inverse limit. So So here's what Dijkgraaf-Witten theory assigns to a manifold M. You look at this space parameterizing all G bundles on M. Every G bundle on M gives you a one-dimensional complex vector space by this construction. And then you take sections of the corresponding bundle. OK, so to explain why this is a topological quantum field theory, I should explain this not just as a collection of vector space invariants for manifolds individually, but I should explain how it's functorial with respect to Bordisms. So what happens if you have a Bordism from M to N? So I don't want to erase this. Let's go over here. So let's say that M and N are manifolds of dimension n minus 1. And I give you a Bordism between them, which is an n manifold with boundary B. So now let's consider G bundles on all of these manifolds. We can look at maps from M into BG, maps from N into BG, and maps from B into BG. So this is a classifying space for G bundles on the entire Bordism. And every G bundle on the entire Bordism gives you a G bundle on M and a G bundle on N. Now, I told you that there are vector bundles, or sorry, there are one-dimensional local systems L sub M and L sub N on these mapping spaces here. Now, what happens when you have a Bordism? Well, you could take these local systems and you could pull them back to B. So that gives you two different local systems on maps from B into BG. And you can think about these two different local systems as given in the following way. So on the space of maps from B into BG, cross B, you have an n-dimensional cohomology class. You can then either integrate that over M or integrate that over N to get a one-dimensional cohomology class, which gives you a local system. But inside B, M and N are homologous. B itself is a homology from M to N. And that tells you that the cocycles that you produce via this construction are going to differ by a coboundary, which means that these two local systems, when you pull back to this space here, they're going to be isomorphic. So let me just write L sub B to mean the common pullback of these two local systems here. So now what we're supposed to do is produce a map from sections of L sub M to sections of L sub N. So the idea is, well, you take a section of L sub M, you pull it back to get a section of L sub B, and then you push it forward to get a section of L sub N. And now we come to the thing that I want these lectures to be about, which is, well, where does the ability to push forward come from? So I defined Dijkgraaf-Witten theory on an n-1 manifold to be given by the h upper 0 of a local system. It's degree 0 cohomology. And in cohomology, you can pull back classes. But if you want to push forward classes, then you could do that if you were talking about homology. But in cohomology, you generally don't have the ability to push forward cohomology classes. So in order to carry this construction out, you want to be working in some kind of setting where there isn't much of a difference between homology and cohomology. So this happens to be such a setting, and let me spell out for you concretely what's going on that makes that happen. So first, maybe I should mention, there's a dual construction. You can talk about the degree 0 homology of X with coefficients in L. And, well, in terms of the abstract description, that's just the colimit of the diagram L. But if you want to know what it is concretely, well, what you do is you take the direct sum of all of these vector spaces L sub X, and you mod out by relations that tell you that for any path and any vector in this vector space, it should be equal to its image under this isomorphism. So let me say what that is more concretely over here. So let's assume, so let's let X be something like maps from M into BG. So what's important about this space that lets this? What's going to be important is that this is a space with finitely many connected components, and each one of those components has a finite fundamental group. Or, well, it's sort of also important that it has finite, its other homotopy groups are also finite. In this case, the higher homotopy groups all vanish. So what does this look like? X looks like a disjoint union of over all isomorphism classes of G bundles P on X of the classifying space of the automorphism group of P. So these are all finite groups. And in the case where M is connected, these are all groups that appear as subgroups of G. So now let's suppose, so let's say X0 be a connected component of X. And let's choose a base point on X0. So then X0, it looks like the classifying space of a finite group, which is the automorphism group of a G bundle, but let me just call that group H. So now we can take our local system L sub M, that's a local system on this mapping space, and we can restrict that to X0. And I told you earlier that on a connected space, giving a local system is really the same thing as giving a representation of the fundamental group. So we can think about this thing as a representation V of the finite group H. And now, in these terms, what are we doing? Well, if you take H naught of this local system, let me only look at the restriction of this local system to X0. Well, this is just the invariant part of the vector space G. This is just the collection of all vectors V. Oh, sorry. The H invariant part. This is the collection of all vectors V such that HV is equal to V for all H. That's what degree 0 cohomology computes in this case. So there's a dual construction. You can talk about the homology of this local system. And what you get is the space of coinvariance for the action of H on G, on V. So this is V mod everything of the form HV minus V, where H is in H and V is in V. So we get very lucky in this circumstance. So note, there is a canonical isomorphism from V lower h to V upper h. Well, maybe there's two canonical isomorphisms, but the one I'm thinking of is the one that's given by the norm map. So suppose you wanted to make invariant elements of G, of the vector space V. Well, there's an easy way to do that. There's a map from V to itself, which just takes a vector little v and adds up all of the elements in its orbit, averages over the group to produce a new element of V. Now, the new element you produce is always going to be H invariant. So this map actually factors through the subgroup of V consisting of H invariant elements. And by the same token, this factors through the quotient factors through the formation of co-invariants. Because this averaging map, you can just observe, it annihilates everything of this form. So that induces a map from co-invariance to invariance, and this is called the norm map. And now, the thing that we need to use in this context, so if M is an abelian group, well, let me make this remark more generally. So if M is an abelian group acted on by a finite group H, then we can define invariance and co-invariance as on that other board. And there's a natural map between them called the norm map, given by that construction on the other board. And this map is not always an isomorphism. But it is an isomorphism when you can divide by the order of the group H. So this often has an inverse. Given by taking an element x to x divided by the order of h. If that's allowed, well, if you start with an invariant element, divide it by the order of h, and then apply this averaging construction, you get the element back again. So whenever you can divide by the order of h, this map is an isomorphism. In our case, we can do that because we're talking about complex vector spaces. So note that if you explicitly write down what you're doing when you invert this map, it involves dividing by the order of certain finite groups. And that explains sort of expressions like this that will appear in the formulas for the numbers that you get at the top level. But at a lower level, in terms of wanting to produce this thing as a functor, you're not hitting the thing you're worrying about has a slightly different form. You're not explicitly worrying about whether or not you can divide by the order of a group. Rather, you're explicitly worrying about whether or not you can. This map is an isomorphism. If this map is an isomorphism, well, what it tells you is that taking homology and taking cohomology are the same thing. And then you get to pull back because you're talking about cohomology and push forward because you're talking about homology. That enables you to make lots of constructions, and those are the constructions that you need to make in order to build this thing as a functor. Yeah?
A little bit more about that word often. Like,
Often, well, OK. This has an inverse given by x goes to 1 over h if multiplication by the order of h from m to m is an isomorphism. So there's a precise statement.
One other question. So far, everything you're doing looks like it would work for a compact link group. You can certainly define this push-pull. You've got these classes on DG. You wouldn't have quite the same decomposition of the mapping space, but
well, I mean, this is a sort of purely algebraic thing.
Right,
and
right.
I mean, Dijkgraaf-Witten theory, the version for a compact Lie group is Chern-Simons theory, and it's a much more sophisticated entity.
Is the breakdown just in the decomposition of mapping space, and it's just higher topology that I'm not being careful with?
The breakdown is, well, I think there's a lot of breakdowns.
Okay. All right, I'm thinking about the integration now. That's what
Yeah, I mean, there's some kind of integration, but it's a sort of a topologically flavored integration. So this is a purely algebraic story. All right, so this is now all I want to say about Dijkgraaf-Witten theory. So I told this story because I wanted to motivate that you should be interested in the norm map and when it's an isomorphism. And having norm maps be isomorphisms enables you to construct some interesting mathematical objects, Dijkgraaf-Witten theory being an example. Are there any questions? Do you feel motivated? All right. So, oh, wow. All right, so, oh no, I don't want to erase this.
I do have a question.
Yeah.
So the stuff that's coming along now, before the end, is that something that someone could then go back to this Dijkgraaf-Witten style thing and sort of, are you promising us that whatever you're going to do also has sort of Dijkgraaf-Witten style applications?
Yes, the theorem that I am going to tell you about at the end implies that you can do Dijkgraaf-Witten, you can construct analogs of Dijkgraaf-Witten theory with fancy coefficient systems, some fancy coefficients. But I have nothing to say about what those constructions give you. From now on, the interesting theorem is that, well, that it's possible to make them, say. Okay, so we're starting again. And here's the basic question that I want to talk about from now on. So I want to talk about when can we say that the homology of a local system is isomorphic to its cohomology. And for right now, by homology and cohomology, I just mean degree 0 homology and cohomology, which in this is given by this formal procedure. Cohomology means take the inverse limit. Homology means take the direct limit. So I want to be in the situation for this discussion of C being an arbitrary category. So later we'll consider some special values of C, like we can take C to be the category of sets or abelian groups or complex vector spaces. But for right now, let's just say C is any category. Well, maybe not any category. Let me say it's a category with limits and colimits, so that homology and cohomology are well defined. So let's talk a little bit about local systems with values in C. So the first observation is that they form a category. So for any space X, the collection of local systems on X, and here I mean with values in C, but I won't write it. So this forms a category. And I'm going to write that category as C to the X. Because how do you describe a local system? Well, for every point of X, you give an object of C. So you can think about it as a functor from the fundamental groupoid of X into C. But I'll just save some chalk and think of it as some kind of a map from X into C. So now, I want to ask now how this category depends on X. So let's suppose that I give you a map from X to Y of topological spaces. Well, something I've already been using is the fact that it makes sense to pull local systems back. If you have a map from X to Y and you have a local system on Y, you can pull it back to get a local system on X. So a map from X to Y determines a functor, I'll call it F upper star, from C to the Y to C to the X. And what is this functor given by explicitly? Well, if you have a local system L on Y, and you pull it back, that's a local system on X. So to describe it, I need to tell you what you're going to assign to every point little x. And we'll just take L, whatever that does at the point F of X. OK, so you can pull local systems back. And now, if now using the fact that C has all limits and colimits, you can deduce that this construction has both a left and a right adjoint. So F upper star has a left adjoint which I'll denote by F lower shriek. So that goes from local systems on X to local systems on Y. And a right adjoint. F lower star, which goes from local systems on X to local systems on Y. So in category theory language, these constructions are given by taking a left Kohn extension along the map from fundamental groupoids from fundamental groupoid of X to the fundamental groupoid of Y. Or sorry, this one's the left Kohn extension, this one's the right Kohn extension. We can be more explicit about what these functors are given by. So let's assume that F is a fibration for simplicity. Then we can just write formulas for what this push forward does. The push forward of L, in the shriek sense, at a point little y, this is just given by taking the homology of over the inverse image of that point with coefficients in L. Or maybe I should say L restricted to this inverse image of y. And the analogous, you have a precisely analogous formula for what the other push forward does, except instead of taking homology, you take cohomology. So one of these push forwards involves taking homology along the fibers. One of them involves taking cohomology along the fibers. And maybe I should just mention, as an example, if y is a point, then c to the y. Local systems on a point, you just have to specify an object of c. So this category is equivalent to c. And then if you look at the projection map from x to y, well, f lower star of a local system is just what earlier I was calling the cohomology of that local system. And f lower shriek of a local system is just earlier what I was calling H0, homology. So we have this cohomology and homology construction. These are just relative versions or fiber-wise versions of the same constructions. So now let me go back to this question. And this is really the question that I want to answer. But in order to address this question, or to talk about isomorphisms of homology with cohomology, I want to address a more general question, or a relative version of that question. I want to address the question of when I can say that these two functors are the same. So let me just rephrase that. When can we say that f lower shriek is isomorphic to f lower star for some map f from x to y? OK, so what I'd like to do now is give you a construction of an isomorphism between these two functors, or an attempt to construct an isomorphism between these two functors. Let's see how much time I've got. Oh, almost no time. So what makes the most sense? I could give you a construction right now, and it won't be very comprehensible, but you could mull it over for a day, and then I could give it to you again on Friday. Or we could just start taking questions now. What do you want? The first one, OK. All right, I'm going to give you an opaque construction. So here is an attempt to define an isomorphism of f lower shriek to f lower star. So without loss of generality, everything I'm talking about from now on it's a homotopy theory business. So without loss of generality, I can replace x and y by homotopy equivalent spaces and arrange that f is a fibration. That's just going to be something convenient for what I'm going to write now. I want to consider the following diagram. So let's think about x going to y by the map f. And let me think about x going to y also by the map f. And let's form the fiber product. So this is x cross y, cross over y with x. So this has two projections onto x, which I'll call pi1 and pi2. And there's one other thing I want to think about, which is the diagonal embedding of x into this fiber product. And note that if you compose that with either projection, you just get the identity map from x to itself. So let's assume our attempt to define an isomorphism is not going to start from nowhere. We're going to assume that we've already done that for delta. So let's assume that we have an isomorphism between the two push forwards for delta, and we'll try to construct one for f. OK, so here's the construction. What I'm actually going to construct is not necessarily an isomorphism, but is going to be an analog of that norm map that I discussed earlier. So remember what happened when you had a finite group acting on some representation. You could take invariants and you could take coinvariants, which are like cohomology and homology. And you had a norm construction that went from coinvariants to invariants, or from homology to cohomology. So we will construct a natural transformation. Let me call it norm, which is going to go from f lower shriek to f lower star. So the first observation is that to give a natural transformation from f lower shriek to f lower star is the same thing as to give a natural transformation from the identity functor to f upper star, f lower star. This is just by the definition of f lower shriek. It's defined to be the adjoint of f upper star, which in particular tells you this. So I can think about that norm map as a map from the left-hand side to the left-hand side, or I can think about that norm map as a map from the identity functor to this composition. So we want to make a map from the identity. Well, now I should be careful. What category am I talking about? So I'm talking about the category of local systems on x. So let's take the identity functor from that category to itself. And I'm going to construct for you a natural transformation from that to f upper star, f lower star. That's the wrong way for a map to go, which is why this is we're constructing something interesting. OK, so what do we do? Well, let's look at this diagram. We're constructing a map from local systems on x to local systems on x, but I want to think of the first x as here and the second x as here. So one of the functors that we're thinking about is first push forward along f and then pull back along f. So first go here and then go here. The other functor that I'm considering is the identity. But I want to think about the identity as starting here, pulling back along the identity map, and pushing forward along this identity map. So let's write that. Well, the identity functor is obtained by first pulling back along the identity functor and then pushing forward along the identity functor. But let's factor that, because using through this map delta. So what do? I first pull back along the projection pi1. And then I pull back along that diagonal map delta. And then I'm supposed to push forward along the identity map, which I do by first pushing forward along delta and then pushing forward along the second projection. All right, and now I want to use that assumption that I had over there that push forward and pull back along delta, or sorry, that the two different push forwards along delta are the same. So let me identify this with the same thing, but with a delta lower shriek instead of a delta lower star. All right. But delta lower shriek, delta upper star maps to the identity functor because those functors are adjoint. This functor is by definition the left adjoint to this one. So this maps to pi2 lower star composed with the identity, composed with pi1 upper star. So what's that? That's first pull back and then push forward. But I can do those in the other order. I could have first pushed forward and then pulled back. So this functor is just isomorphic to f upper star, f lower star. So here's a map from the left-hand side to the right-hand side. It's an element, it's a natural transformation from this functor to this functor, which is the same data as a norm map from f lower shriek to f lower star. So let me now just give a definition which I'll elaborate on in my next lecture. So definition. We will say that f is ambidextrous if 1, the diagonal map from x to x cross y over x is ambidextrous. And 2, well, I need to say a little bit more to make this make sense. We're going to define the notion of an ambidextrous map. And for any ambidextrous map, we're going to define an isomorphism between the two push forwards. So here's the definition. We'll say f is ambidextrous if first the diagonal map is ambidextrous. And that in particular tells us that push forward, the two notions of push forward along the diagonal are the same, which gives us this norm map from f lower shriek to f lower star. And now we will, that gives us a norm map. It doesn't tell us that the norm map is an isomorphism, but we will say that f is ambidextrous if that norm map is defined and is an isomorphism. So this definition, obviously, is circular. But another word for this kind of circularity is this is a co-inductive definition. So what I mean by that is this. The collection of ambidextrous maps is the smallest collection of maps that contains all homotopy equivalences and has this closure property, that whenever the diagonal map is ambidextrous and this construction gives you an isomorphism, then we will also say that f is ambidextrous. So this should be opaque, and in my next lecture, I will hopefully make it much less opaque and convince you that this is a very natural thing. OK, that's all I got.
Questions?
Yeah?
Say if f is mapping from like a connected space to another connected space.
Uh-huh.
Is it going to be equivalent to say that the homotopy fiber of f is finite in the sense that?
So, oh yeah. So the question is, well, not getting into the exact specifics of the question is, does this reduce to some kind of finiteness of the fibers of f? And the answer to that question depends on C. So really, I should have said f is C ambidextrous if this construction produces an isomorphism. And which maps are C ambidextrous will depend on C. So the case that you might be interested in is where C is something like complex vector spaces, in which case C will be a map will be ambidextrous if its homotopy fibers are classifying spaces of finite groups, for example. But in the next lecture, we'll talk about what ambidexterity means, thinking of this maybe more as a property of C than a property of F. For different values of F, what conditions on C do you meet when you require F to be ambidextrous?
Yeah.
you are saying that so you are saying that you have a normal because of one. Part one.
Yeah, part 1 gives you this isomorphism.
That isomorphism should be normal, so it came from somewhere.
Exactly.
Okay.
So you start with a homotopy equivalence, where there's an obvious equivalence between the lower shriek and lower star because they're both inverses to the pullback. So now that lets you define a norm map whenever the diagonal is a homotopy equivalence. That norm map may or may not be an isomorphism, but if it is, then that might enable you to construct some more norm maps. And then if those are isomorphisms, then you can produce some more.
Okay. Come as a system.
Yeah, it's so in the end, if you want to prove that maps are ambidextrous, well, there's a whole lot of constructions to unwind because the definition of each of these maps involves looking at the inverse to the previous norm map that you constructed.
Other questions? Well, let's speak again.